Question 9. Two particles, P and Q, start moving along the x-axis at time t equals 0 and never meet. Particle P is initially at x equals 4 and its velocity v at time t is given by v equals 2t plus 4. The position of particle Q is given by x equals 1 plus 3 times log base e of t plus 1. The diagram shows the graph of x equals 1 plus 3 times log base e of t plus 1. Part A. Find an expression for the position of P at time t. We are given an expression for the velocity of particle P with respect to t, and we have the velocity v is equal to 2t plus 4. To find an expression for the displacement or the position of particle P with respect to t, we need to find the primitive of 2t plus 4. In other words, we integrate v with respect to t. So the position x is equal to the integral of 2t plus 4 dt. Performing the integration, we get x is equal to t squared plus 4t plus c, and the c is the constant of integration which we will need to find. Now we are given a clue. We know that when t is equal to 0, x is equal to 4. In other words, the particle initially is 4 units from the origin. So substituting 0 for t here and here, and 4 for x here, we can form this equation. 4 is equal to 0 squared plus 4 times 0 plus c, and solving for c, we get c is equal to 4. Therefore, x is equal to t squared plus 4t plus 4, where x is the position of P at time t. Part B. Copy the diagram into your writing booklet and, on the same set of axes, draw the graph of the function found in Part A. From Part A, the expression for the position of particle P at time t is x equals t squared plus 4t plus 4. Now this is a quadratic expression whose graph is a concave up parabola. Now it's also worth noting that t squared plus 4t plus 4 can be factorized as a perfect square, and we get x is equal to t plus 2 in brackets squared. Now I've already stated that the graph is a concave up parabola, but the vertex is at negative 2, 0, and the y-intercept is 4. But we're only graphing for values of time greater than or equal to 0. So here is a sketch of both of the graphs, x equals 1 plus 3 times log base e of t plus 1, which was originally given in the question. But this is the graph here of x equals t squared plus 4t plus 4, which was the expression that we found in Part A. Notice that I've started from the y-intercept of 4 because we're only graphing for non-negative values of t. Part C. P and Q are joined by an elastic string and M is the midpoint of the string. Show that the position of M at time t is given by x equals 1 over 2 times open bracket t squared plus 4t plus 3 times log base e of t plus 1 plus 5 close bracket. The position of the midpoint M, which I've denoted with an xm, is the average of xp and xq. Now xp is the position of particle P with respect to time, and xq is the position of particle Q with respect to time. And to find the average of xp and xq, we add them together and divide by 2, or we add them together and multiply it by 1 over 2. Now xp is t squared plus 4t plus 4, which we found in Part A, and xq is 1 plus 3 times log base e of t plus 1. So xm is equal to half times open bracket t squared plus 4t plus 4 plus 1 plus 3 times log base e of t plus 1 close bracket. Now 4 plus 1 is 5, so they're two like terms that we can combine. And we get half times open bracket t squared plus 4t plus 3 times log base e of t plus 1 plus 5 close bracket as required. Part D. Find the time at which the acceleration of m is 0. Consider particle m. Now from part C, the expression that gives us the position of particle m is x equals 1 over 2 times open bracket t squared plus 4t plus 3 times log base e of t plus 1 plus 5 close bracket. Now in order to find an expression that gives us the acceleration of particle m, we differentiate x with respect to t, which gives us the velocity of particle m. Then we differentiate again to give us the acceleration of particle m. So in effect, we're finding the second derivative of x. So differentiating x with respect to t to get an expression for the velocity of particle m, we get v is equal to x dash, which is equal to 1 over 2 times open bracket 2t plus 4 plus 3 over t plus 1 close bracket. And that's equal to 1 over 2 times open bracket 2t plus 4 plus 3 times t plus 1 in brackets to the power of negative 1 close bracket. Now expressing this term here using a negative index just makes the next differentiation a little easier. So we're going to differentiate v with respect to t to find an expression for the acceleration of particle m. So the acceleration a is equal to x double dash, which is equal to 1 over 2 times open bracket 2 plus negative 1 times 3 times t plus 1 in brackets to the power of negative 2 close bracket. And using positive indices, that's equal to 1 over 2 times open bracket 2 minus 3 over t plus 1 in brackets squared close bracket. Next, we solve the equation a equals 0 to give us the value of t, or the value of time, when the acceleration of the particle is 0. So we're solving 1 over 2 times open bracket 2 minus 3 over t plus 1 in brackets squared close bracket equals 0. Now multiplying both sides of the equation by 2 to eliminate the fraction 1 over 2, we get 2 minus 3 over t plus 1 in brackets squared is equal to 0. Now multiplying all terms by the denominator t plus 1 in brackets squared, we get 2 times t plus 1 in brackets squared minus 3 equals 0. Now moving the negative 3 on the left hand side over to the right hand side, it becomes positive 3. So the equation becomes 2 times t plus 1 in brackets squared equals 3. Dividing both sides of the equation by 2 to isolate t plus 1 in brackets squared, we get t plus 1 in brackets squared is equal to 3 over 2. Then taking the square root of both sides of the equation to isolate t plus 1, we get t plus 1 is equal to plus or minus the square root of 3 over 2. And subtracting 1 from both sides of the equation to isolate t, we get t is equal to negative 1 plus or minus the square root of 3 over 2. But we know that t must be greater than or equal to 0. So we discard the negative value of t, that is the value of t which is negative 1 minus the square root of 3 over 2. Therefore the time when the acceleration of m is 0 is t equals negative 1 plus the square root of 3 over 2, which is around 0.2247 and so on. Part E. Find the minimum distance between P and Q. The distance between P and Q is given by xp minus xq is equal to t squared plus 4t plus 4 minus open bracket 1 plus 3 times log base e of t plus 1 close bracket. Expanding the brackets, we get t squared plus 4t minus 3 times log base e of t plus 1 plus 3. Now we get the plus 3 from 4 minus 1. So differentiating the difference xp minus xq with respect to t, so differentiating this expression here, we get 2t plus 4 minus 3 over t plus 1. Next, we solve the equation xp minus xq in brackets dash, so the derivative 2t plus 4 minus 3 over t plus 1 equals 0. Multiplying all terms by the denominator t plus 1, we get 2t times t plus 1 in brackets plus 4 times t plus 1 in brackets minus 3 equals 0. Expanding the brackets and collecting like terms here, we get 2t squared plus 2t plus 4t plus 4 minus 3 equals 0, which simplifies to 2t squared plus 6t plus 1 equals 0. So we have a non-monic quadratic equation, so using the quadratic formula, we can solve for t. We get t is equal to negative 6 plus or minus the square root of 6 squared minus 4 times 2 times 1 over 2 times 2, which simplifies to negative 6 plus or minus 2 times the square root of 7 over 4, which simplifies further to negative 3 plus or minus the square root of 7 over 2. Note that both values of t that we just found are negative, which do not exist, since the value of time t must be greater than or equal to 0. Now, the curves x equals t squared plus 4t plus 4 and x equals 1 plus 3 times log base e of t plus 1 never meet and diverge. In other words, they get further and further away from each other for t greater than or equal to 0, which can be observed from the graph that we sketched in part B. And that's this graph here. So we can see that the two curves diverge, they get further apart from each other as time goes on. Therefore, the minimum distance occurs at time t equals 0, which is given by 4 minus 1, which is equal to 3 units. Going back to the graph that we sketched in part B, that's the difference between the two y-intercepts. So 4 minus 1 is equal to 3. As a side note, for values of time t greater than or equal to 0, it can be shown that the value of the derivative of t squared plus 4t plus 4 is greater than the value of the derivative of 1 plus 3 times log base e of t plus 1. Recall that t squared plus 4t plus 4 gives us the position of particle p with respect to t, and 1 plus 3 times log base e of t plus 1 gives us the position of particle q with respect to t. And showing that the derivative of one is greater than the derivative of the other for all values of time greater than or equal to 0 is one way to show that the two curves diverge using calculus.